Hi guys, welcome to part 2 of our matter and energy unit. I'm going to finish up today just reminding you about the different types of matter there are. And mostly today we're going to talk about, in this video we're going to talk about energy. So there's your different parts of matter. All matter is either a pure substance or a mixture. Pure substances are elements or compounds, and mixtures can be homogeneous or heterogeneous. So looking at a sample of copper and tin. Bronze is an alloy. It's made of copper and tin. And so find the total mass of the sample. Easy enough. 68 plus 7, 75 grams. So how do you find a percent? Just a reminder from the last video, take your part divided by your whole. So for copper, it'll be 68 divided by 75. Gives you a percent of 90.7%, and for tin it's everything else, so 9.3%. So if you remember back from the other video, we could take those percents and then look at a different sample. So how many grams of each element does a 346 gram sample of bronze contain? Well, the answer is you don't know, because unlike our compounds from the previous slide, this is an alloy, and an alloy is a mixture, which means every alloy, every mixture, either whether it's homogeneous or heterogeneous, can be completely different. Think about it like sweet tea or Kool-Aid. Sometimes you go over to somebody's house and they have really good Kool-Aid because they put a lot of sugar in it, whether you go to somebody else's house and they didn't put much sugar in it, so the Kool-Aid's crappy. Now here they actually do the calculations, but we're not going to worry about it. Alright, so if you can put mixtures together by just mixing them up, then how can you separate them? Well, once again, if you can do it physically, then you can separate them physically, which means you don't need a chemical reaction. If you have big things in a mixture, you can do it by sorting, which is just size and shape. Color, size, shape, texture. You sort Legos, or you sort the change in your pocket and things like that. But we really don't use that in chemistry much, because most of the things we use are really, really small. One thing that we can do the common way to separate things in chemistry class is by filtering. And filtering is just separating things out by their particle sizes. You think about a water filter. A water filter is going to let water go through because it has small particles, but then it doesn't let larger particles go through, things like dirt and sand. You can separate by a magnet. The problem with separating by a magnet is one of your two things has to be made of iron. So that's a really good way to separate things. If you have iron, we have an example of it in class, but if you don't have iron, it doesn't really help you much. Now, some of you have taken biology before, some of you haven't. If you've taken biology before, one process that they separate mixtures is a process called chromatography. And some of these pictures might look kind of familiar. Okay, on the left here, and then kind of redone on a computer on the right, if you remember, if you've taken biology, these are called gel electrophoresis. And so what this does is it separates out based upon how well DNA strands are going to be dissolved in water. And it separates out the different parts of the DNA strand based upon how much they'll dissolve. This right here is called paper chromatography, and what you do is you spread some green pigment from a tree or a leaf onto this paper and then let water flow up through the paper, and then while it flows, some of the pigments are going to dissolve better than others, and it's going to separate out onto the paper, so you get a rainbow of pigments. Alright, so another way you can separate mixtures is by density. The easiest way is, will it sink or will it float? You throw a bunch of things in the water, things that sink are going to sink, things that are going to float. Separation based upon density. You can separate based on, like oil and vinegar. You separate, just let them sit, they'll separate themselves because of their density. But you could also use a centrifuge, and a centrifuge is just going to spin tubes around. The more dense thing in the mixture is going to go to the bottom of the centrifuge, and the less dense thing will go to the top. This is what they do with blood. If you want to separate out blood, you can centrifuge it. The heavy red blood cells the dense red blood cells will go to the bottom, and the not dense plasma is at the top. This is how you separate out blood when you give doubles. You can also use density to what's called decant. So if you have a mixture where there's some visible particles that are in some water and they're all at the bottom, well, if you pour very, very, very slowly, then you're going to pour the water off of the top of the other particles. But it's not perfect, and so we don't use that much. Another process, and a very common process in chemistry, is distillation. Now, if you look at this word, distillation, hidden here in the middle of it is the word still. And if you think about not like staying still, but what a still is, an object called a still, some of my folks that are watching this video might know better than others, but if you know what a still is made to make used to make moonshine. And so what you do is you put your fermented liquid into it, and then you boil it, and the first thing that boils off is alcohol. And so that's how you make really high powerful alcoholic drinks in a still, and a separation based upon boiling points. You can also do this just boiling off water. So if you have salt water mixture, you can boil the water, collect what condenses off, you'll have water over here, and you'll have just salt left over here. Now, these have nothing to do with chemical reactions, so you don't need chemical reactions to separate the mixtures. These substances are not bonded, so you can separate them out. Just most of these you just separate out by sorting. But another example is dental amalgam. Dental amalgam is used for your fillings, and this is why if somebody gets struck by lightning or like a lot of electric shock, their fillings can actually pop off because they separate out, because it's a mixture. It's not a chemical compound. It's a mixture that they use for fillings. All right, so let's talk a little bit more about density. Density is how tightly packed particles are, and there's two parts to density. You have mass and you have volume. Now, if you look at that formula there, mass is on top of the fraction, volume is on the bottom of the fraction, which means the more massive something is, the more mass, the more matter it has inside of it, the higher its density, and the more volume something has, the bigger it is, the lower its density, because the bigger you get without as much matter, you have a bunch of empty space. So D equals M over V. Some folks don't like algebra much, so we got this little trick here for you. You take this formula and you write it in this triangle, and then all you have to do is cover up what you're looking for to get the answer. So if you're looking for density, cover it up, mass divided by volume. If you're looking for mass, cover it up, density times volume. And if you're looking for volume, cover it up, mass divided by density. So that's kind of a little algebra trick to help you so you don't have to think too much and you can just plug numbers into a calculator. Most of the time, units for density are going to be grams over centimeters cubed for solids, which we don't really use that much because we don't use centimeters cubed, or grams per milliliters for fluids. Now, what is a fluid? If a solid is a solid, we all know what that is, then fluids are everything that's not a solid, which leaves you with liquids and gases. So most of the time in this class for density, we're just going to use grams per milliliter, even if it's a solid, because we're going to measure it using fluids. Here, you're going to notice that in just a second. So how do we find volume? Well, since probably about 5th grade, you've been finding volume using a formula. So you just multiply all the sides, length times width times height. You probably got a little bit fancier in about 7th or 8th grade and said power squared times height, which is pretty much the same formula, just circle instead of a square. Now, we don't use these in chemistry class, really hardly at all, because most of the things we have are not going to be nice, pretty, rectangular solids and cylinders and things. Most of the things we deal with in chemistry class just don't have a good shape to them. So how do we find this volume? Some of you probably screaming the answer out already. Well, how we do it is water displacement. So here's what we do. You get some water, a known amount of water, call that my initial volume, and then you throw your unknown object, in this case a trumpet, into the water, and then what's our volume? It's how much the water moved. So what you're going to do is you're going to take your final volume, subtract it from your initial volume, and you have the volume of my object. We have a lab we're going to do where we're going to work on all kinds of objects that we need to find the density of this is the main way you're going to find density. Now, the density of water, oddly enough, is just straight 1 gram per milliliter. And this comes from the fact that they defined a gram by how much a milliliter of pure water weighs. And so, actually, I'm sorry, they defined a milliliter by how much space 1 gram of water took up. And so that's why density of water is 1.0 grams per milliliter. And that makes life pretty easy because anything that is lower than 1 is going to float, and anything that's higher than 1 is going to sink. So let's do some examples here. We got some nice 4x4 boards here. Now, if you know anything about wood, you throw it in the lake or river or stream, and it's going to float. Density less than 1. Now, we got any golfers watching this? They know exactly what happens when you hit a golf ball in the water, and unfortunately for the golfers, they're going to sink. The density is greater than 1. But ping pong players, they got a little bit better because ping pong balls, they float. Density less than 1. Now here's an odd one here. When you think about an aircraft carrier, you think about something that's really, really heavy. You think about something that's really heavy and is going to weigh a lot, but we're looking at a picture right here of it doing what? Floating on water. It's floating on water, which means its density has got to be less than 1. Now, how is that possible? How can the density of this aircraft carrier be less than the density of this golf ball? Well, the answer is it's huge. Look at it. So its volume is also really, really large, which means density is less than 1. So density of a liquid and solid, just about constant. And that's what we're going to be dealing with here in this class. Density of liquids and solids don't really change. If I tell you the density of a compound and it's a solid or a liquid, that's always going to be the density of that compound. Gases, on the other hand, they do a little bit different. The gases will actually change density based upon their temperature. And this is why, because their volume changes as their temperature changes. If you when you blow up a hot air balloon, you're not adding air to the hot air balloon. You're adding heat to the hot air balloon. And so that's what's happening there. All right, so let's do some density calculations. A sample of lead has a mass of 22.7 grams and a volume of 2 milliliters, 2 centimeters cubed. Find a sample's density. So we have mass and we have volume. Simple enough. D equals m over v. Cover up the D, m over v. And we're going to say 22.7 divided by 2. Piece of cake. Smash those buttons on the calculators and you get 11.35. Don't forget your unit. Grams per centimeters cubed. Another sample of lead occupies 16.2 centimeters cubed of space. Find the sample's mass. Now, I just told you it's a solid. Its density is constant, which means that's our density of lead. So we know our density. We know our volume. Density times volume equals mass. So we're going to say 11.35 times 16.2. And if you look at this, centimeters cubed is on the bottom. Centimeters cubed is up here on the top. They cancel out. We'll be left with grams. 184 grams. And you can pause the video and do these problems right here if you want to. It's good practice. Like I said, we're not going to be doing this in chemistry class. Or this. All right. So let's talk about properties. You have chemical properties and you have physical properties. Chemical properties tell how a substance reacts with other substances. Physical properties can be observed without chemically changing the substance. So a physical property would be your hair is brown, your hair is long. I can cut your hair. It's still hair. I can cut it. Rock and roll. Physical property. A chemical property tell how a substance reacts with other substances. So whether or not your hair will catch on fire, that's a chemical property. What happens after I pour acid on your hair? That's a chemical property. Those chemical properties tell how a substance reacts with other substances. Then we have extensive and intensive properties. Most of the properties we're going to be dealing with in this class are intensive. They don't depend on how much you have, but you had things like mass and that are going to be extensive. How much you got matters. So let's do some examples real quick. Electrical conductivity is a physical property. intensive property. It's physical property. You don't change the wire when you shoot electricity through it. Reactivity with water. There's a buzzword. Reactivity. How will it react? That is a chemical property. Chemical and intensive. Heat content. Total energy. Now there's a buzzword. Total energy. How much energy you're holding, how much stuff you've got. That's an extensive property, but you don't change it when you see how hot it is, so it's a physical property. Ductility is a word that means you can be pulled into a wire, can be drawn into a wire. It's still the same thing, even though you put it into a wire, physical property and intensive. Malleability, you can hammer it into shape, physical, intensive. Now, the opposite of malleability is brittle. So a malleability means you can hammer it and it bends, it doesn't break. Brittle means you hammer it and it just shatters. Still a physical property, still intensive. Magnetism. When you use a magnet, it doesn't chemically change. Physical property and intensive. All right, so let's roll through our solid, liquids, and gases real quick. So what is solid, liquid, and gas? I mean, you guys know what it is because you've been doing it since about kindergarten, but why is something solid, liquid, and gas? Well, it has to do with how the particles are moving. Solid particles are just vibrating. They're just moving back and forth. That's all they're doing. You think about, well, you look at a table. Well, that table's not moving. Well, its particles are moving. All particles in the universe are always moving. How the particles move tell you whether it's solid, liquid, or gas. Solid particles vibrate back and forth. Liquid particles just move around. It's what's called translating. Translating just means moves around. Now, liquid, to be liquid, you move all around, but you never get away from another particle. You're always close to another particle. So you're translating, but close together. And then gases, you translate, but you're far apart. These guys don't care about the other particles. They just move around wherever. Water particles, they always stay close to each other. So how do we change states in matter? Now I'm going to just roll through this real quick because some of them you already know. If you're going from solid to liquid, you melt. If you're going from liquid to solid, you freeze. Liquid to gas, boil, or vaporize, or evaporate. Gas to liquid, condensation. Solid to gas, sublimation. That's one of the new words there you probably need to learn. Sublimation. Things do go solid, straight from solid to gas. The most common one that you've probably seen before is dry ice. Dry ice is not ice, it's frozen carbon dioxide, and it goes straight from a solid to a gas. And once you freeze that dry ice, that carbon dioxide, it's going to go back from a gas to a solid. That's called deposition. Now, if you notice, there's these giant arrows at the top and the bottom here. These are all going to be about energy. So as you go from solid to liquid to gas, your particles are moving faster, so you're gaining energy. Energy is put into the system. And as you go from gas to liquid to solid, you're losing energy. Energy comes out of the system. So what is energy? Energy is the ability to do work. Potential energy is stored energy. Now, in your middle school classes, you probably talked about stored energy, potential energy being the rock at the top of the hill that's about to roll down the hill. In chemistry class, though, and really in the universe, potential energy is stored in bonds between atoms. If you want to get energy out, you break bonds. You release those bonds. And some examples of that is in food. When you eat food, you chew up the food, but that's not when you get the energy. You get the energy when those food particles get broken down into small little chemicals, and then to remember cellular respiration for my biology people, those small little chemicals get broken into even smaller chemicals. Those bonds get broken, you release energy. It's the same thing that's happening in your car with gasoline. You put the gasoline in your car, you burn the gasoline, that breaks bonds, released energy. Same thing in batteries. It's a chemical process inside of batteries. The bonds are being broken. Now, once things start moving, you got kinetic energy. Now, if you notice, remember, I already told you one time, kinetic energy, all particles in the universe are moving. All atoms everywhere are moving all the time. How fast they're moving is the kinetic energy. And you can measure that with temperature. Hot gas particles move faster. That means they have more kinetic energy. We're going to talk later in the year about something called average kinetic energy. And that's the exact same thing as temperature. Now, one of the cool things about energy is it's just like matter. You can't get rid of it. You can't make new energy, and you can't get rid of old energy. So let's look at hydrogen and oxygen. Hydrogen and oxygen are both gases, and their bonds have lots and lots of energy. So when I set hydrogen gas on fire and turn it into water, this is what happens. We go from really high energy particles to really low energy particles. Now that energy had to go somewhere. When you set hydrogen on fire, what do you get? You get a lot of energy comes out. What does energy look like? It looks like boom, woof. It looks like explosions. These two examples right here are both examples of this chemical reaction. And the energy is coming out. In this case, good that the energy is coming out because it gives the space shuttle power to leave the atmosphere. In this case, bad because the Hindenburg was filled with hydrogen. Somebody lit a cigarette, boom, there it went. So another example, combustion of acetylene. The heat, the light, the sound is that energy coming out. Endothermic versus exothermic. Endothermic is when energy goes in, the beaker feels cold because energy is leaving, it's taking energy away from your hand. Exothermic, the beaker feels hot because energy is coming out. It's going to give energy to your hand and make your hand feel warm. There's just some examples. We'll talk about some more of that in class. And that's a good place to stop right there, guys. That is your, I know, I'm sorry it was fast there at the end, but feel free to go back and look at this video anywhere you want to. That was your Unit 2 in chemistry. I'll see you in class.